for water to come up into an estuary, and how long does that water stay in the estuary, and then how long does it take to come out of the estuary, which is really important when you think of storm surge modeling. So that kind of puts all this work into context. So many years ago, we were thinking about flushing times and how long it takes water to come in and out of an estuary. And now we're trying to get to the point of, do we know how much sediment is going to accumulate onto a marsh, and therefore does a marsh survive through time? Dr. Erin Peck is a recent graduate from the Oregon State University, and she's a coastal geologist and now is doing a postdoc. This is her second postdoc, and she is an expert on the Pacific coast. So we needed to get that Pacific coast influence because we want to understand wetlands across the entire country, coastal wetlands. And so her influence on this team is to bring us that coastal perspective from the Pacific coast. So let's talk about tidal wetlands and what do they provide as a list of services and why are they beneficial for us. So in a nutshell, they provide protection from the coast due to flooding and erosion. They are a habitat location for a wide range of species and have large biodiversity. They provide a wealth of recreation and economic opportunities for the huge population growth that's happening along all coastlines around the world. And just within North Carolina, there are over 7,500 miles of wetland shoreline just in our state alone. So if you think of just one state, that's a lot of miles. And so we wanted to study every state in the coterminous United States. A big undertaking. How do you wrap your head around one model that can do that? And again, this is a rapidly expanding population growth area. And ultimately, at the bottom, there's the arrow that says sediment supply is the critical factor to survival of wetlands. So we need to know more about this sediment source and the supply of sediment. There are several types of tidal wetlands. The dominant type along North Carolina's coast are salt marshes. These all are along rivers and creeks behind barrier islands. They're in the bays and the river mouths, and of course, all along the coastal plain. They exist of grasses and other emergent plants that can thrive in salt water. But there are also these very narrow fringes. So you can imagine, like in the upper right picture, there are these big swaths of salt marsh, but in other locations, they are just some narrow fringing habitats. We also have tidal wetlands that are freshwater forests, and also freshwater marshes that are still tidal. These can consist of bottomland hardwood forests, some marsh fringing marshes, and of course some evidence that what were once freshwater environments that are now salty are the ghost forests and ghost trees that we hear about all the time in the news. So these locations tend to be inland from the salt marshes. They're mainly found along the Atlantic and Gulf coast. You won't find these along the Pacific. And that freshwater environment that is affected by the rise and fall of the tides. They're very highly productive and diverse in their plant species, and they're an important habitat for a wide variety of birds. We can't forget about mangroves. They're a tidal wetland that's important mostly in Florida and some parts of the other parts of the Gulf Coast. These are salt-tolerant trees, and you can see by these pictures that the most important part from a biodiversity standpoint is what you can't see below the water. These plants and this environment exports a large amount of organic matter that's really important in supporting the food web and the adjacent estuaries. And of course, their main benefit to all of us is they are a great protector of inland areas from storm surges. So I apologize, this one's a little bit blurry, but this is another slide that shows you the benefits of wetlands. There are a variety of benefits, including the wildlife, the ecosystem, the storm surge protection, etc. So how do these environments interact from a watershed perspective? We have the ocean at the bottom of the slide. I don't see my little arrow moving on here. Oh, there it is. There we go. Here's the mouth of the estuary. Along notice it's a much wider water body, and we have this tidal saltwater coastal wetlands. And as we move upstream, we get into further upstream where it's tidal freshwater environment, narrower streams, until we get to the head of tide. And then above that, this is where there's no longer any saltwater influence. And then we get non-tidal wetlands above that. So just to give you a geography of what the coastal wetlands look like. So how do these wetlands change through time and space as a response to the changing sea level? There are two ways that marshes and wetlands can change when sea levels change. The first is they can migrate, and that means it's a lateral migration. They can move forward and backward depending on sea level rising or falling. The second way that marshes and wetlands can keep pace with sea level is accreting, or moving up and down. And we call that amount of space that's taken up with this accreting upward or downward is called the accommodation space. It's that amount of space that a wetland can either move laterally or vertically. So think of that volume of space is what is available to a wetland to have at its disposal in case the water level is to rise. And if water level does rise, what we need to have in order for the wetland to survive is a amount of sediment accumulation that's equal to or greater than the amount of sea level rise in order to sustain itself. The two other factors, of course, that affect this lateral movement include the terrain, right? How steep the terrain is, the topography, and the land cover. So if there's a lot of man-made influence and there's a barrier to movement, then the lateral movement can't take place. So we all know that sea levels are changing around the world, and these maps can be obtained from NOAA. Here's an example just of the North Carolina coast. And you can see that these sea levels do vary quite dramatically, especially even between Wilmington and the Outer Banks. And this data is all available, and you can see that it's at specific locations where they have really good tide gauges where they can measure these and calculate the trends in millimeters per year and then predict out into the future. So knowing this about wetlands and how they can react in space laterally and vertically and what their environmental needs are to sustain themselves, we asked this question: how much can contemporary, meaning recent, fluvial sediment load offset the relative elevation loss of tidal wetlands occurring due to relative sea level rise? That's our main question, right? How much of contemporary fluvial sediment load? Now you might be saying, well, why is she saying fluvial? She keeps saying fluvial, she keeps saying fluvial. Our model that we're talking about today does not account for other sources of sediment. It doesn't account for marine sediment or estuarine sediment that might get stirred up from the existing sources of sediment and deposited back onto the wetlands or onto the marshes. This is only coming from rivers and streams. So our goals to address this question were to use public data. That was the first one. To create a model that could automatically derive this total amount of accumulated sediment for all tidal wetlands. So that was important, that we needed to create, if we were going to do this across the entire country, we didn't want to do this manually. That would be way too labor intensive. We had to do it automatically in a model. And our point was to study the whole country because there are lots of tools out there and lots of models out there that just do one watershed at a time. We wanted to do the whole country. And then, if you're going to have ambition, right, you might as well go for it. So then we wanted to then, of course, see how well the model was performing. And then we wanted to get the results published out onto an online environment. So again, it was really important that we have a model that has some transparent data processing, use publicly available data so that it's repeatable. And also, if the public data gets updated, you can just run it again. and that it's applicable, that this model could work nationwide. And then lastly, we're going to talk about what are some of the concerns and drawbacks that we discovered. So those are the overarching approaches and what our question was. So what was this set of data? And you can imagine, we thought about a lot of, over the last couple of years, we thought about a lot of different data sources we could use. And ultimately, in the model I'm going to talk about today, the results I'm going to present today, these are the data that we use. So the first is the USGS data set called SPARROW. Has anybody heard of SPARROW? Yay, we got two. You know, that's probably one of the most underutilized USGS data sets out there, and hardly anybody uses this data set. So if there's one take-home message, write down SPARROW. It's a super cool data set. It does have the sediment load attribute data that I'm going to show you, but it has a wealth of other data in that data set as well. So if you're interested in nutrients like phosphorus, nitrogen, things like that, the SPARROW data has that as well. So that's our source that we use because it's nationwide. It's not consistently the same nationwide, but it's still nationwide. And it was a data source from a federal agency that's gone through a lot of quality control rigor already. We also use the NHD plus HR version 2 data for all the hydrography. We used NWI wetlands data. Now we could talk about the pros and cons of NWI data. That was definitely something we chatted about for a very long time, and whether we should try to use other wetlands data. And I can go at length about why we ended up using NWI data, but anyway, that's what's in the model right now. And the NOAA, two sources of NOAA data that we used are the sea level rise shoreline positions that are different at different sea level rise scenarios. And then we also use the NOAA projected rate of sea level rise data that I'll show to you. For assessment, we went through a whole slew of places to ended up finding 93 different locations across the country that have marker horizon-based measurements of sediment accumulation. And these are the best ways of measuring sediment accumulation in marshes. And so those were sort of used for our assessment purposes in the model. This is a really simplified workflow that kind of just puts it down into the nuts and bolts of how those data were used to basically produce a map that shows sediment accumulation and compared that to sea level rise prediction, and then said whether or not the marshes had enough sediment accumulation to keep up with sea level rise. So again, the geographic area are the regions defined by the USGS SPARROW data, and the geographic units varied, but so because of that varying geography, we processed everything by hydrologic unit code. So here's a model. You can see what the model looks like in the little, that's the iterative model that runs for every HUC in the country, every hydrologic unit code in the country. Here's what the USGS SPARROW regional approach looks like. Those are the regions. So when I say the Midwest, what I'm talking about is really Louisiana. The Midwest is, of course, the whole middle part of the country, but according to SPARROW on the Gulf Coast, that's actually the Midwest region of the Gulf Coast. And those are all the other regions that we looked at. So there's the Pacific Coast, the Southwest, Midwest, Southeast, and Northeast. So there's 5 regions in the SPARROW data. There's a website to get the SPARROW data if you ever want to look at it. And looking at it a little bit closer, here's a map showing delivered accumulated load for the whole southeastern region. And you can see, right, that a lot of it's relatively small in the yellow, but it accumulates in the rivers, right? That's why you can see the rivers popping up on this map. It is important to point out, if you're using the SPARROW data, that you have to look at each region independently because the regions don't all have the same attributes. But if you zoom in a little closer, this is what that SPARROW data looks like. It's essentially aggregating all of the USGS stream gauging data for the entire country and all of their sediment samples that they have for the entire country that have been aggregated over a 12-year period to the Huck 12 level of geography. So if you look back, oops, sorry, it's only going one direction. Oh yeah, sorry. Oh no, how do I go backwards? Oh, there we go. Okay, so you can see the whole region here, right? And then if you go in, you can see it's really at the Huck 12 level. Okay, so here's the NWI data. I'm sure almost everybody in here has looked at Fish and Wildlife Service NWI data. So you can see in this map that the wetlands that we care about at the highest level of detail are the blue and the green way down at the coast. So even though we're analyzing all of those regions across the whole country, when you boil it down to tidally influenced wetlands, we're talking about those blue and green wetlands along the coast. Here's the national hydrography data, and these are really complicated again, so we had to identify all of the tidal streams. And in doing so, we came up with two approaches for modeling tidally influenced streams. Those are the terminal paths and the level paths. And if you've ever looked at all of the hundreds of attributes on national hydrography data, think of those as unique identifiers for a terminal path is a larger river system, and you can see that in that's a terminal path. And the level paths are the smaller creeks. So we wanted to analyze sediment delivery to the larger systems as well as the little creeks. Here's the NOAA sea level rise data. It's delivered essentially in a CSV file. You can turn it then into these grids. We used the 2020 modeled. This is all modeled data, right? And you can see the model in the graph. And we used the 2020 median data. So you can see that right there, which points to. So that was the scenario that we used for our initial run of the models. To calculate the sediment yield, sediment load, and then ultimately the thickness of the pancake, these are the equations we used for both the terminal path and the level path. So what do the results look like? Is there enough riverine sediment to sustain wetlands? So by region, everywhere that's above the dotted line are places that are achieving enough sediment, and below the line they are not. So the bottom of each band is the predicted amount, and it gets a little complicated, but what we did is we added in the error that's in the SPARROW data, which is quite a bit of error. And so what you have is, here's our prediction. We added in the error for the SPARROW data, which gives us a band. And then we added in the lighter area, which shows if we just limit all of our data to just 150 meters of the estuary center line, how much more error do we get onto that estimate? Just to see how much error could possibly be in our model. Here's the results for the level path analysis. So in red are all of those hydrologic units that are below the global sea level change amount. So they do not keep up with sea level rise, everything in red. Everything in orange might keep up with it, and yellow is doing fine. That's the level path analysis. This is the mean average for the hydrologic unit. The terminal path, you're probably saying it looks pretty similar. Here's what they look like together. So there's only 3 hydrologic units out of those 53 that there's a difference between the terminal path and level path. But it does get a little bit more complicated. So we had to look into whether or not, when we give this data to people to look at, whether they should use the terminal path results or the level path results. And after a lot of work, I don't need to go into all this, we have come up with the solution that if watershed size is less than 21 kilometers squared, you should use the terminal path, right? Really small watersheds, and much bigger watersheds, bigger than 21 kilometers squared, you should use the level path results. Let's keep going, because I'm running out of time. Okay, so let's show you what some of the data looks like. Those are all the tidal creeks and rivers in the southeastern region, to just give you an idea what this data looks like. That's what it looks like when you zoom in on an area. Everything in red are the wetlands that are going to not keep up because they do not have enough riverine sediment. Now, they might get sediment from the marine source, right? They might get an estuarine or marine sediment source, but just from the riverine upstream source of sediment or upland sediment, there's not enough. So I just highlighted a couple of places, and I'm going to skip this because I'm almost out of time, right? Okay. Okay. So what are the main conclusions? Here's my conclusion. Of the 4,798 rivers that are in the U.S. coastline, 74% do not carry enough sediment to keep up with the rate of sea level rise. Why is this important? If you're asking questions like, will removing a dam liberate enough sediment to save a wetland? Or will stormwater retention ponds trap too much sediment? Or can accelerated erosion from land clearing, increase sediment to help a wetland? This data will help you because this mass balance calculation provided by this model quantifies how important it is for river sediment load. You need to have this mass balance calculation to put into the measurements into a proper context. You have to have this mass balance in order to form discussion of management and related decision making. And I'll just end it with, there is a website if you feel like looking at the data, but let me just put up the acknowledgements and ask for questions. Oops. Sure. Because we didn't have any SPARROW data for those 2 regions. They were determined by the hydrologic unit code, the watershed boundary. Yeah, that's a USGS watershed boundary. Yeah, you're welcome.
It's kind of cool because I was here all day and listening to all this.
I'm sorry I went over.
No, you're fine. I just like she's a smart lady, so definitely get up with her while we're here at the conference. And if not, afterwards, go UNCW, right?
Yeah, please feel free to email me.
Okay. Thank you, Doctor.
Thank you.